Hey guys, and welcome to this video on solving systems of equations by graphing. So let's get this show on the road. Alright, earlier in the year, we discussed solutions to equations with just one variable. For example, 2m plus 4 equals 10 plus 4m, and I'm sure you know how to solve that. Here, solutions were just single numbers that, when substituted in for the variable, made the equation true, and we could always check our solution. So indeed, -3 was the solution to that equation because it was the number, such that when we substituted it in for the variable, made the statement true. We've also discussed solutions to equations with two variables. For example, y equals -6 plus 2x. Here, we were looking for x, y ordered pairs, such that when we substituted each of the values in for their respective variables, the equation was made true. Of course, there were infinitely many ordered pairs that made this statement true, so there were infinitely many ordered pairs that were solutions to the equation. So instead of listing them all, we represented them using a graph. If you're an ordered pair on that graph, then you're a solution to this equation. If you're a solution to this equation, then you're an ordered pair on that graph. Now we're going to start solving systems of equations. First, let's define what a system of equations is. A system of equations is any set of two or more equations involving the same variables. To be a solution to a system of equations, an ordered pair must make all of the individual equations true at the same time. So here's an example of a system of equations. 2x plus y equals -1, and x minus y equals -5. It's kind of like there's an and in between them. Remember, to be a solution, you've got to make both of these true at the same time. That is, we're looking for an ordered pair, x comma y, such that when we substitute those values in for x and y in both equations are made true. Well, we know how to represent all the ordered pairs that are solutions to the first equation. That's just going to be a graph of a line. So let's go ahead and graph it. Alright, so this graph in red represents all the solutions to that first equation, 2x plus y equals -1. Now we know how to represent all the ordered pairs that are solutions to the second equation. That's also just going to be a line. So let's go ahead and graph it. Alright, so this graph in blue represents all of the solutions to this equation in blue. Well, we see that these two lines intersect right here at the point -2, 3. This means that -2, 3 makes the equation 2x plus y equals -1 true, and the equation x minus y equals -5 true. That means that ordered pair is a solution to both equations. Therefore, this is the solution to our system of equations. And so our first strategy for solving a system of equations with two variables is simply graph all the solutions to each individual equation, and any point where all the graphs intersect represents a solution to the system of equations, because that point will make all the equations true at the same time. All right, time for some practice. Now I'd like you to try to solve this system of equations. Once again, our general strategy is to graph each of these equations individually, and any place where all of the graphs intersect will be an ordered pair that makes both of these equations true at the same time, and hence that will be a solution to this system of equations. A couple notes. You can graph these however you'd like, right? We've got a lot of strategies for graphing lines. You can use any of them. And one word of caution is, please take your time and graph these as accurately as possible, because if your graph isn't accurate, they might intersect at the wrong place, and you might get something that actually isn't the solution. So why don't you pause the video, solve this system of equations, and then play the video when we're done, and we'll reconvene. And so we see, after graphing each of these individual equations, we get two lines that happen to intersect right at the ordered pair 2, 6. So 2, 6 is the ordered pair of numbers that makes both these equations true at the same time. That's the solution to this system of equations. Note, always a good idea to check our answer. All right, just another practice problem. Why don't you pause the video and please solve the system of equations using the exact same strategy as before. All right, so after graphing each of these individual equations, we got two lines that intersect at the point 6, -4, and that ordered pair made both of those equations true at the same time, and we checked it, so that's our solution to this system of equations. All right, two more examples, and each of these are going to be very interesting and different from the ones we've done before. So why don't you take a second to pause the video and solve this system of equations using the exact same strategy we have before. So in this example, when we graph each of these equations individually, we see that they don't intersect ever. They're parallel lines. Therefore, since they don't intersect, there is no ordered pair that makes both statements true at the same time. So there are no solutions to this system of equations. And when we look at the two equations in slope-intercept form, it's obviously impossible that y, some number, could possibly equal 2 plus 2x, and also -3 plus 2x. It's impossible. It can never happen. That's why there's no solution to this system. That's why these two graphs are parallel lines and never intersect. Which brings us to a definition of an inconsistent system of equations. We say that a system of equations is inconsistent if it has no solutions. So we would say this system of equations is an inconsistent system. All right, last example. Again, please pause the video and try to solve this system of equations using the same strategy we've been doing this whole section. All right, so in this example, when we graphed each of the individual equations, we got the exact same line. And if we look at the slope-intercept form of the two equations, we see that these two original equations were actually the same equation all the time. It was the exact same equation twice, it just looked a little different. So note that any ordered pair that makes one of these equations true automatically makes the other one true. And since there are infinitely many solutions to either one of these equations, we'd say that there are infinitely many solutions to this system of equations. Which brings us to our next definition of a dependent system of equations. We say that a system of equations is dependent if it has infinitely many solutions. So we would say that this system of equations is a dependent system. One note, it might be tempting to say all real numbers as our solution set, but that's not the case. It's not that any ordered pair is going to be a solution. There just happen to be infinitely many ordered pairs that are going to be solutions to this system of equations. So what we do here is we do want to say infinitely many solutions, but we want to describe this solution set to the reader. And to do that, all we need to do is actually just write one of our original equations from our system. And that tells the reader there are infinitely many solutions, and they are all the solutions to the equation 6x equals 2y plus 8. Alright guys, that's it for this video. I hope you found it helpful, and I hope you enjoyed.